Okay, so here's where we were last time. We were talking about Green's theorem, and let me remind you, Green's theorem happens in two dimensions. Right? This is so it's peculiar to R2. There are kind of like it in R3, but Green's theorem itself specifically happens only in R2. Okay, we'll talk about the three-dimensional kind of equivalent things later, including later today. So here's our idea. The big conclusion was that we started with this idea of what it means to talk about a boundary of a curve, and then we found this sort of complementary idea of applying this thing called Green's operator to a vector field that has the neat effect that when you take a boundary of some two-dimensional region and then you take Green's operator of some vector field, the line integral of the vector field over the boundary, the double integral of Green's operator over the original region, always the same. Okay, so fits the pattern of our, this is our continuing rip-offs of the fundamental theorem of calculus. Okay, so we saw an example last time where we were looking at a curve that is the unit circle going counterclockwise. We used it to turn a line integral into a double integral. Right, so the line integral turns into a double integral, and the double integral ends up being really easy. So it worked out super well. And now we're going to move on to the next example. So here, another line integral that we're going to compute with a double integral. Here's our vector field. Is what it is. And then let's see, we have a curve that consists of straight line segments starting at the origin and then going in succession to several points and then back to the origin. So here's a picture of our curve. It starts at the origin and then it goes like that and then like this and then like that and then back to the origin. Okay. So there's our curve. And we want to compute, again, this line integral. Okay, so now, big reminder, one of the conditions, the big catch on Green's theorem is that Green's theorem allows you to compute a line integral only if the curve is a boundary of some two-dimensional region. Again, not a technical requirement. It has to be a boundary of a two-dimensional region because you need that two-dimensional region over which to do the double integral. Not only is the theorem not true if it's not a boundary, it doesn't even make any sense if your curve is not a boundary. Right? Okay, so we worried about that in the case of this first example, and easy to persuade ourselves a unit circle is a boundary. But this wacky curve, really got to worry about it. Now, it's tempting to say that it's the boundary of, this, I don't know, you might call it a triangular figure eight. It's tempting to say it's the boundary of that region, but it's not. This curve is not the boundary of that region. The boundary of this region is oriented the wrong way on that piece, the wrong way on that piece, and the wrong way on that piece. Right? So again, this word boundary is a finicky thing at this point. When we say boundary of a two-dimensional region, we mean not just curves, but curves with orientations. And the orientations are wrong over here. Okay, so how do we fix this? Well, it turns out there's a clever fix. The clever fix is to say, well, let's not look at D2. If we look at this region D2, it's oriented the wrong way. Let's look at negative D2. Right? So D2 with the negative orientation. And keep in mind that, have a negative orientation, that means everything just goes backwards. So the boundary of negative D2 is, well, going the correct direction on all three of those edges. So the boundary of negative D2 combined with the boundary of positive D1 in fact gives us our entire curve all oriented in the correct direction and everything works. Okay, everybody on board? So our curve is not the boundary of, just D1 plus D2. It's the boundary, as it turns out, worrying about orientations, it's the boundary of D1 minus D2. Okay, so going back to the algebra, recognizing that our curve is a boundary. All right, can rewrite the line integral as specifically a line integral over a boundary, suitably interpreted. Line integrals on boundaries are double integrals of Green's operator. That's just invoking Green's theorem. And Green's operator, if you take our given vector field here, there's our vector field, and you plug in and compute Green's operator, you get 1. Easy calculation. By the way, in case I didn't say this last time, make sure that you memorize the formula for Green's operator. Right? It's the magic formula that makes Green's theorem work. So, dq dx minus dp dy. Make sure that you're ultra solid on that memory. Okay, yeah. So Green's operator. Plug that in. Now, note we're evaluating over d1 minus d2, so we're doing the integral over d1, and then we're subtracting the integral over d2. And not hard to persuade yourself that these two integrals, well, each of these integrals represents an area. d1 and d2 have the same area, and so the difference is 0. And so that integral is 0. So, lovely little calculation. Now, you might say that, well, hey, this, I wasn't that scared of this vector field. It's not that bad. It's just pretty easy to write down. And that's true. It's not such a bad vector field. But if you wanted to brute force this, there are 4 separate line segments. And so you would have to write down 4 separate integrals. 1, 2, 3, and 4. So instead of doing 4 line integrals, we did 1 double integral. Okay, another example. I'm going to let y'all read on your own. So I made the observation last time that when we use Green's theorem, often, and in some sense most of the time, we use it that way, in the sense that we want to know the value of a line integral, and we compute that line integral by using Green's theorem to turn it into a double integral. This is just how it tends to be. Most of the time, it's useful in this context of, I need to compute a line integral. Hey, look how convenient, I can instead just compute this. Not always. I'm going to show you an example where it's useful going the other way, and that is computing an area. If you want to compute an area, there is an application, kind of a clever twist on Green's theorem, that allows you to compute area. Area, of course, being a double integral. So the trick is to use this vector field that has this convenient feature that Green's operator is equal to 1. It's convenience. Let's see what happens as a result of this. Keep in mind this area, that's a double integral of 1. That's a double integral of Green's operator. Right? Because we just agreed that for this vector field, Green F is 1. That then gives me the line integral of the vector field around the boundary. And this vector field, not hard to persuade yourself, this vector field, specifically the vector field 0x, an alternative way to write that is, remember that our dx vector has components dx and dy, scalars, and so just x dy. So I'm writing it in this coordinate notation here because this is a very common way to write this particular line integral. If you don't like it, you're very welcome to just write it like this. It's a little more to write down, though, in this case, and in this instance, you kind of see the convenience of that notation. So anyway, nice punchline. If you want to compute an area of some region, here's a line integral that will compute that area for you. Real slick move. Now, so you say, well, yeah, but area, gosh, that's a high school geometry problem, and this is a multivariable calculus problem. It kind of seems like we're making life harder, not easier. Point point of view, it depends. But let me just point out what a nasty problem this could be. Here is a region that has, let's see, 1, 2, 3, 4, 5 different edges, right? How would you compute the area of this region? Well, gosh, I mean, I guess you could chop it up into triangles, but these aren't right triangles, and they're not 30, 60, 90s or anything recognizable. It's not clear how you'd go about computing the areas of these 3 triangles like that. So another neat fact, and this is one that I'm going to suggest that y'all prove on your own. This integral x dy, if you were computing that integral on a straight line segment, there's a really easy formula for how to compute that integral. It's just the average value of x times the change in y. That's 3-function arithmetic. Well, okay, 4-function arithmetic. You got to divide by 2 to get the average, right? But it's really easy arithmetic. So, very handy fact. Now, this proof is an exercise. It's really kind of a chapter 5 exercise. If you think about it, all you have to do to prove this is take a line segment that starts at the point x1 and y1, ends at the point x2, y2, parameterize that line segment. Y'all remember how to parameterize lines, right? It's a chapter 1 thing. So parameterize this line segment from that point to that point, and then just compute this straight out of chapter 5, plug and chug from the parameterization. It's just details. This is what you end up with. Okay, so I think everyone should do that. It's a nice little practice problem. Okay, so that being the case, we have what is in fact an easy formula to compute an area. It's just integral x dy. Well, I should say it's an easy formula for computing an area of a polygon, because that integral x dy is super easy to compute on the line segments in question, and they're just arithmetic then. So here's how it breaks down for this particular polygon. You have 5 different edges. Let's look at this first edge, L1. Right, it goes from 1, 1 to 2, 2. And this integral from 1, 1 to 2, 2, x bar delta y, the average value of x is 3/2. The change in y, well, y starts at 1, ends at 2, therefore average value, the change in y is 2 minus 1. Easy arithmetic. And then likewise going around the remaining edges, the next edge here, that's from 2, 2 to 4, 0. That integral computed by that arithmetic, and etc. Going on around, you add all this up. A little bit of arithmetic, a little annoying, admittedly, but it's better than your alternatives, right? And there's your answer. Very convenient. Yeah, everybody good? All right. Okay, so that's all I'm going to say about Green's theorem right now. We will be coming back and talking more about Green's theorem a little bit later on. Some ideas I'm kind of procrastinating until later, but this is a good first start on Green's theorem. And we're going to move on now to Gauss's divergence theorem. This is one of the big ones. The physics applications of Gauss's divergence theorem are tremendous. Very, very important. If y'all have taken a if you've taken a Physics 1, Physics 1 or Physics 2, if you take an E&M, for example, lots of uses of Gauss's divergence theorem. Now, they don't say Gauss's divergence theorem in that context because you haven't had multivariable calculus necessarily when you take that class, but they're actually using big applications of Gauss's divergence theorem. I'm going to show you some of those today, time permitting. Okay, so here's our scenario. We're in R3 now. Now remember, here's our R3 diagram as it stands, right? And we have, these conventions of, what kinds of evaluations we have in these different dimension columns. So, points, curves, surfaces, three-dimensional solids. We're going to consider our usual scenario of we have some vector field. We have some domain. Now, in this case, it's going to be a three-dimensional solid in R3, in column 3, I mean. And we're going to consider what happens when you take a boundary compute the corresponding, whatever the diagram says. The diagram says, let's take our vector field, and on that boundary surface, let's compute the flux. Just following the pattern. Fingers crossed, hoping something nice works out. And we're going to ask, is it possible to come up with something here from the vector field that would have the feature that, when you do a triple integral over the original domain, that I would get the same thing. Right? So, said differently, we're going to be looking at a domain, we're going to be looking at a three-dimensional region, and on its boundary, we're going to be looking at fluxes. And I would like to realize that as a triple integral. So I want to think of that as something that adds up over the entire interior of the solid. So no surprise, the first step is to look at the solid, and let's think about, well, what happens when you take a solid like this and start chopping it up into little pieces, right? Like such as this one and that one, etc. Right, so just following the pattern of what's happened in the past, I know that because I'm looking at boundaries of these little pieces, what I want to know is it true that the boundary of that thing plus the boundary of that thing plus the boundary of this thing, when I add up the boundaries of all these different things, do you get that beautiful interior cancellation where all the interior faces and edges disappear and you're left only with the boundary of the original region? In other words, do boundaries accumulate? That's going to be essential in our consideration. And the answer is yeah, it does. Right? Now you just got to look at the picture and just kind of think through the geometry of it. Let's take this one at a time. Let's start with our, I'm going to look at just two little boxes next to each other. We're going to start off thinking about this one. Right? Let's talk about the boundary of that. Well, the boundary of that thing consists of this face oriented that way, and this face oriented that way. Right? Remember, the rule for boundary of a given thing is always away from where the solid is. And then this face oriented that way, etc., and among which is that face oriented that way. Okay. All right. Well, now let's think about this piece. That box. Let's think about its boundary. Well, its boundary, again, consists of a bunch of faces. There's that piece of the boundary oriented that way. This piece oriented that way. Etc., a bunch of other faces, including this face oriented that way. Right, so thought of as part of the boundary of D2, the orientation on this interior face is that way. So when you add up, we got two rectangular boxes here. Each box has 6 faces. These that makes a total of 12 faces, right? But only one of those faces appears twice. That is this face. Let me make a better color choice. This face, which thought of as part of the boundary of D1 is oriented that way. Thought of as part of the boundary of D2 is oriented that way. And so when you take boundary of D1 plus boundary of D2, you have two terms that include this face. They have exact opposite orientations. They cancel. Right? So this is kind of a, you might say, a three-dimensional kind of analog of what we saw in the case of Green's theorem. With Green's theorem, we were looking at two rectangles, not boxes, just rectangles. And we noticed that, well, the way orientations go, right? We end up with that edge oriented two different directions. This edge appears twice as part of the summations of the boundaries, and opposite orientations cancel. Right? And so therefore the boundary of this chunk plus the boundary of that chunk is the boundary of the union. Well, it's the same thing here for this solid. The boundary of this left half of the solid plus the boundary of this right half of the solid, interior face cancels. Different geometry to the cancellation, right? But nevertheless, cancellation, the interior face disappears and you're left with just the boundary of the original solid. Everybody happy with that? So I argued with, in the case of Green's theorem, that this oversimplified picture here, well, there's only one interior face. What if there's lots of interior faces? Each interior face cancels for the exact same reason. You draw a picture that has a bunch of them, and they all cancel. And likewise here, it's harder to draw a three-dimensional solid. It's been chopped up into a lot of little pieces, interior faces shared on either side. It's really hard to do with a pencil. Right? So I didn't draw that bigger picture, but you can it's kind of we can sort of cheat on this picture here a little bit, and let's look at, for example, let's see here. I'm going to draw. Let's see here. There's a lot to. So there's a top box and a bottom box, and let's think about this shared face there. That shared face is part of the boundary of this, oriented down. Oh, I should do this with a pencil. Thought of as part of the boundary of this piece, it's oriented downward. Thought of as part of the boundary of this piece, it's oriented upward. Same deal, appears twice, opposite orientations, cancels. This is going to be the same game for all the interior faces. Okay. All right, so that allows us to start with the same sort of an argument that we previously did. Analogous argument we just showed that the boundary of an entire solid region is the summation of the boundaries of all the little boxes that you get when you chop it up into little pieces, right? So the total boundary is the sum of the little boundaries. That being the case, the flux through the total boundary is the same as the sum of the fluxes through the little boundaries. Okay, so that's where this first equation comes from. This is true no matter how you slice it. Therefore, you take a limit. You're taking a limit of a constant, which, of course, does nothing. So that's free. This is starting to look kind of like a triple integral. Not exactly a triple integral, though, of course. So I need to multiply and divide by volume. As, again, total rip-off of an idea that we've done several times before. Now you look at this expression, that really looks like a triple integral. We're taking a limit where we add up over all of the little boxes that you get when you slice up your three-dimensional solid of some expression times volume. That's the total Riemann sum for a triple integral. Okay. Skipping over some formalities. So rewriting this as a triple integral, the remaining question is, but what is this integrand? Now let me remind you, we got lucky once, twice, where when we ended up with the integral on the right-hand side, it's like, oh, hey, check it out. It's something we're familiar with. Cool, it's derivative. Or, hey, how convenient, it's gradient vector. That was totally lucky, right? You can't expect to always get that lucky. And in this case, we don't get that lucky. Right? This is not an expression that we happen to already have recognized. Nevertheless, this is something that can be calculated. It's not something I want to focus on in this course. It's kind of details. There is a homework exercise where you're going to kind of do a plausibility argument on the formula I'm about to show you. Anyway, for the purpose of this course, I'm just going to cite that this integrand here can be computed with this formula. That's called divergence. Let's see, where did I write that? Divergence. So given a vector field, keep in mind P, Q, and R are the components of the vector field F. This vector field, of which we're doing a flux around the boundary, P, Q, and R. The divergence is computed by doing the x partial of P, the y partial of Q, the z partial of R, and adding those up. Details as to why that works. Okay, so there you go. So this thing, because of this theorem, computed by that. So this formula, that formula, and this is Gauss's divergence theorem. Note it has all the earmarks of the fundamental theorem of calculus and Green's theorem and the fundamental theorem of line integrals, in the sense that there's two terms that are equal to each other. Right? One is over a region, the other is over the boundary of that region. Over the boundary, you're looking at some integrand. On the original solid, you're looking at some sort of a derivative of the integrand. Right? In this case, it's not the gradient, it's not the derivative, it's not a Green's operator, it's a new thing called divergence. So a little bit of notation now. So this is very commonly abbreviated as div, short for divergence, of course. Pretty reasonable notation to call it. There's another notation. Now I have to kind of segue into this next bit of notation. Y'all remember the formula for gradient, right? That's the gradient, and we have this notation where we use this symbol here to represent that I'm taking partials with respect to x, y, and z, and then making a vector out of them. It's as if we're applying that operation to f. So you give me an f, and what I'm going to do is I'm going to take the x, y, and z partials of them and make a vector out of it. So we're going to pretend like we could reasonably call this symbol by itself this thing, which again, you should be a little uncomfortable with this because I'm using a notation as if this is a vector, right? But a vector, shouldn't a vector have components that are numbers? Right? Here we have a vector whose components are operators, right? So it's a little bit weird to write that down, but nevertheless, it's a pretty convenient notation. It communicates what's happening in that process, and very common, by the way. So this, if you notice, are the three derivatives that are being computed in divergence. Now, you're not taking, as we were in the case of gradient, the x, y, and z partials of all one function. Now, here we're taking the x partial of one function and the y partial of a different function and the z partial of yet a third function. So what we're doing then, it's almost like a dot product. We're doing the x partial of the first component of f, and the y partial of the second component of f, the z partial of the third component of f, and then adding them. It looks awfully similar to a dot product. So that in mind, we actually write it as this divergence. We write it as a dot product, like so. And again, here's there's the del operator. There's the vector field. And we're pairing them up component-wise and adding them. Okay, so very common notation that you'll see, alternative notation for divergence is del dot f. By the way, terminology thing, please don't say gradient dot f, because that's not. Gradient means that you take the del operator and you apply it to a single function in that specific way. This is not del applied to some function that we're dotting with f. This is just del. Right, so you can say del dot f. It would not make any sense at all, and it's not okay to call it gradient dot f. Is everybody comfortable with that? I mean, it looks bad, so be careful with that. Okay, so that's just notation. Here's our resulting theorem, Gauss's divergence theorem. I like to stick it onto the diagram in the usual way. Again, you know what we had previously. This was our R3 diagram. We now have a new operation, divergence, that fits naturally. It's sort of complementary to the idea of boundary in the sense that if you have a solid three-dimensional region and you take the boundary of it, you can then take some vector field and do the divergence of it, and the flux of the vector field through the boundary, the triple integral of the divergence through the solid, over the solid, always the same. So, pattern holds. Yeah, how we doing? Everybody happy? Okay, quick example. All right, so we want to compute a flux. We have a vector field given. We have a surface given. How do you compute this flux? Now, I'll point out, you could view this as a Chapter 5 problem. I strongly encourage you not to. But you could view this as a Chapter 5 problem because, well, you got a surface, parameterize it, plug in the vector field, take a deep breath, and plow forward. But that'd be really hard. Look how ugly our vector field is. It might not look super ugly at a glance, but keep in mind our sphere, our surface is a sphere. That means our parameterization is going to have, take your pick, square roots or trig. One or the other. So these x's, y's, and z's are, let's say, trig functions. So it's going to be nasty if you parameterize. The observation I'll make here is that this sphere is a boundary. Here's what a sphere looks like. And that sphere is a boundary. Specifically, it's the boundary of what we call a ball. Yeah. And note, that's critical to use Gauss's divergence theorem if you want to compute a flux, as we do in this case. You desperately need for your surface to be a boundary of some solid three-dimensional region, because that solid three-dimensional region is going to be the domain for the triple integral that you're going to try to use to compute the flux with. So again, not a technical sort of, worry. This is essential to the implementation of Gauss's divergence theorem. It's got to be a boundary of something, because that something is part of the calculation that comes afterwards. Okay, so fortunately that is the case in this example. We do have a boundary, and so I can write down Gauss's divergence theorem here. Flux over this boundary surface is triple integral divergence. So straight application of the divergence theorem. Then I can take my vector field. Right, here's my vector field. Computing the divergence of it, so that's x partial, y partial, z partial added up. While I'm here, I'm going to go ahead and comment. A very common mistake that I see students do a lot is to misunderstand what divergence is by making these commas instead of pluses. And if you think about it, it doesn't make any sense, right? What would that possibly mean? We'd have a triple integral of a vector field. It doesn't make any sense at all. So don't forget, divergence is a dot product, at least notationally. And more to the point, though, it's a scalar. So you add these three terms. You don't comma these three terms. So this is three different little partial derivative calculations, and you end up with the divergence very conveniently being just 2. So instead of the nasty flux calculation, we just do a triple integral of 2 over the solid ball, and that's easy. Yeah, everybody happy? All right. Okay, so again, you've noticed the pattern. I mean, this Gauss's divergence theorem, it's on the diagram. It's really similar to Green's theorem, which itself was really similar to the fundamental theorem of line integrals. I mean, there's so much pattern here. That said, there are some really peculiarly interesting things about Gauss's divergence theorem in terms of applications to the physical world, because we live in 3 dimensions. Gauss's theorem happens in 3 dimensions. That's the coincidence. So I want to talk about some of those. The first one is really kind of a terminology thing, but this is a really common terminology, flux density, and I want to motivate where this term flux density comes from. Here's a point of view on the divergence theorem, which is there. Remember, flux through a boundary is equal to the triple integral of divergence over the solid. And I want to start by reinterpreting that. Well, first of all, the flux that we're computing, I'm going to use this notation, capital Phi, to represent flux, just to give it a name. And so I'm going to let's reconsider Gauss's divergence theorem as this, this quantity called flux is this triple integral. So I want to start by observing that this thing called flux, we can think of that as an accumulation. And we've talked about accumulations before. Accumulation, like mass, for example, has this feature of accumulation. If you take a mass, some solid thing with a certain amount of mass, if you chop it in half and you look at the left piece and the right piece, well, the mass in the individual pieces, those add up to be the mass of the original thing, right? So mass, it's not like surface area or perimeter or something like that in the process of slicing the problem just fundamentally changes. And, mass is, you might even say preserved or conserved, something along those lines, right? I like the word accumulate, though. So mass accumulates over a region, and I make the observation that so does boundary flux. That's kind of what made the theorem work in the first place. You come back to this part of the derivation, right? Boundary flux is an accumulation of the boundary fluxes over the little pieces, right? The fact that boundary flux accumulates was our first step in getting the theorem in the first place. Here we go. So flux, then, you can think of flux in 2 different ways. On the one hand, you can think of it as, well, we're just looking at the amount of flux in each little piece. But we're also computing it as a triple integral of divergence, and so the case I'll make here is that, well, that means that on each little piece of your solid, we've got this total boundary flux, this accumulating quantity of boundary flux. Well, the amount of boundary flux that there is in each little piece is computed by this formula. It's divergence times volume. And if you look at this then, right, this equation, it says the amount of boundary flux that's happening in a particular little region is this expression times volume. That makes this expression here a density. All right, so remember the term density means stuff per unit volume, in the same sense that mass is mass density times volume. This says that flux, you're going to want to therefore call this flux density times volume. So that's the origin of this term, flux density. It's a very common terminology, flux density, sort of a synonym for divergence. Really common in, the old days, my college days, my second major was in physics, and I heard that term, flux density, in my physics classes about as often, if not more often, than I heard the term divergence. Right, so heads up. You're definitely, a lot of y'all are engineers. You're going to probably hear this term flux density quite a bit. So first observation is make sure you know that flux density just means divergence, but I also want you to kind of get why the term is used in the first place. Now related to that, But I'm a big believer in analogies. I think analogies are great ways to understand things. So I want to go back and talk about the fundamental theorem of calculus momentarily. And fundamental theorem of calculus, recall, says this, right? Yawn, old news. Now let me reinterpret this. Let's view this as that I'm computing this thing called change, which I'm going to denote with the delta symbol. Delta for change. That's nice and all, and I make the observation that, well, furthermore, change is an accumulating quantity. Right? If you have an interval, if the between here and here, these two input values, and here's your A, here's your B. If the function changes by a certain amount between A and B, you could just keep track. Well, how much did it change on the first little subinterval, plus how much did it change on the second subinterval, and the grand total of all those little changes will give you the total change on the interval. So this seems like a little bit of a weird way to think about change, but I think it's eminently supportable, right? That you can think of change as an accumulating quantity. So, that being the case, notice we have two integrals computing change. Said differently, I can think of change as computed with a density. And the same way mass is an integral of, mass per unit length times length. Change is change per unit length times length, or said differently, change is change density times size. All right, so now I know, I feel quite confident that you've never heard derivative referred to as change density, right? Right. How do you choose to think about the derivative? Well, y'all all came into this class as, the primary way that you were thinking of the derivative was slope of the tangent line. Right? Well, I would like to encourage you to reconsider, right? At least supplement with a different point of view. Think of the derivative as being a density. Think of the derivative as being change density. And I'm going to show you a picture that I think makes this very supportable. So here's a figure that shows, on x-axis, and we have, y as a function of x. By the way, this is a graph. This is the familiar picture that we look at when we think about single variable calculus. And let's suppose that my function has a graph that looks like that. Right? And let's now focus our attention on this interval and ask, how much does the function change? Over the course of this interval from A to B, how much does the function change? Well, there it is. That much, right? Function changes like that. No big. Now, let me pose a different question. Can you think of this change as being actually an accumulation of little bitty changes that happened along the way? Well, of course you can, right? On this little piece here, well, there was practically no change in the value of the function on that little piece because it started and ended bound pretty much at the same value, et cetera, et cetera, et cetera, et cetera. I didn't mean to erase that. But then the story becomes a little different once you get into here. As you move across that little subinterval, the function changes pretty significantly, right? Between this point and that point, there's a pretty significant change. Anyway, add it up, the total amount of change between A and B, the total of these incremental changes is the whole change. No surprise. By the way, I like to think of this as, relatable quantities. Like, let's pretend like x represents time, right? And the function f represents like height. You've got somebody who's growing up and maybe their height doesn't change very much, and then they hit a growth spurt, right? And they were this tall and now they're that tall. Right? The grand total height change is the sum of, well, how much did he grow that day plus how much did he grow that day, etc. total change is an accumulation of little changes. So now let me ask yet another little variation of the question, which is, where does this function change? Right, we've got a big change between A and B. The function changes a lot. Where does that change happen? Now, the naive, silly response would be to say, oh, well, we have an interval from A to B, and look, I don't know what you mean by where it happened, but change is computed by f of B minus f of A, and so, it happened between A and B. Right? That's kind of deliberately dense. No pun intended. It was accidental. But let's be honest. But where did the change actually happen? Well, come on. The change clearly happened in here. Look at how much the function's changing for these values of x. Right? That's where the change is happening. Right? If you wanted to describe, at a given point, let's say there, how much change is happening? Well, you can't say change is happening at a single point. At a single point, there's only one. That's just one value. Change sort of means, as you move the input a little bit of, there's going to be a change in the output. So you could talk about how much change per unit size of an interval around here. Right? Change per unit size would be a way of sort of observing that there's more change happening at this point than there is, say, happening at, let's say that point. Okay, so I would distinguish these 2 points from each other by computing change per unit size, which, of course, is going to give you a slope, aka a derivative. Right? As opposed to here at that point, that would be, slope is, call it 0. So the fact that there is a positive derivative here means that there's more, per unit delta x, per unit size, there's more change happening here than there is happening there. Said differently, the change density is greater here than it is there. Said differently again, you can think of this change. We observe change over on the y-axis, but you can think of that change as actually happening over here. And the way I like to think of it is that, there's no change happening along in here, and then there starts to be more change, and then there's quite a bit of change, and then some change, and then it kind of tapers, and again, change over here. So you can think of the change as actually accumulating on the interval, but here's where it really is happening. Okay, so the derivative, aka change density, is a way of measuring where the actions happen. This accumulated quantity of change is really happening there. We observe it over here on the boundary. Yeah, okay, fine. That's a measurement. Let's not be so naive to think that change happens on the boundary. Right? Change happens in a slow progression at places where you can identify. Right? So we observe change on the boundary, but it actually happens in the interior. Okay. So I want to point out that you can talk about that same sort of point of view with divergence and flux. So here's a region. Now I drew a 2-dimensional picture here because the 3-dimensional picture is hard to draw. So let's pretend this is a 3-dimensional picture. All right. Which, fine. So 3-dimensional picture there. Here's the boundary surface. Again, work with me. Let's pretend this is 3-dimensional. And let's talk about flux. Well, flux is measured on the boundary. In the same way that change is measured on the boundary. Right? Change is measured on the boundary. There's a certain formula that happens on the boundary. Flux is measured on the boundary. But again, just because we measure change on the boundary doesn't mean it's actually happening on the boundary. Come on, the change, we agree the change is happening in here. Look at the curve. This is where the person's getting conspicuously taller. You can see it happening. This is where the change is happening. It's happening in the interior, as identified by a particular function called the derivative, which I like to think of as change density. That tells you how much of change is happening at a particular point. The same thing is true here. There is a function that tells you how much of the flux that you measure on the boundary is actually happening in any given particular place in the interior. Now, as I have it drawn here, this is where the flux is actually happening. That's where the flux is being created, this region in here. And I'll walk you through in just a second. But we measure it on the boundary. That's where it sort of manifests itself. But let's not be so naive as to just assume because that's where we measure it, that therefore that's where it happened. That happens in the interior. Okay, now let me try to justify for you now why it's this region in here where the flux is happening. I'm going to look at a little region there, and let's see. In fact, I'm going to zoom in for. There we go. So this little region here, and let's see here. Keep in mind we're talking about flux. Flux is always away from the region, so flux says on each one of these pieces, dot product multiplied by the area, etc. So how much flux is happening on this boundary? Well, I appeal to your observation of what this vector field looks like. On this edge, the dot product 0. Right, the normal vector is that way, the field lines are that way, that's perpendicular, so the dot product 0 on that edge. Likewise on this edge, dot product 0. On this edge, our dot product is of that normal vector with, well, that field vector, and you're going to get a positive flux through that face because dot product's positive. Whoops. But on this edge, your normal vector is that way, the field line is that way, that's negative. And I assert that in fact these cancel each other perfectly because these two normal vectors are pointing in exact opposite directions and they're dotting with the same field vector. Right, so those should cancel. You would expect to get 0 here. Now, critical to this is the idea that the field there and the field there are the same. They have to be the field vectors that I'm dotting with have to be the same to take advantage of the fact that the normal vectors being opposites, the dots give you exact negative values. So the fact that this is a constant vector field is what makes these dot products cancel. Okay. All right. So now let's come over here to this part of the vector field and notice what we have here. The way I've drawn this, our vector field is shorter and then a little longer and then even longer over there. So in this region, what I'm trying to communicate is that I have a vector field where the field magnitude is growing. Again, shorter, longer, even longer. Shorter, longer, even longer. So now let's do a similar kind of a calculation. Let's take a region like this. And let's think about what's going on. Well, the dot product there, this dot product is 0, so there's no flux on that edge. This dot product is 0, no flux on that edge. On this edge, there's a positive dot product. On this edge, there's a negative dot product, but they're not canceling. Because here, look, we're further over to the right on the green edge, and that means this dot product is not only positive, but in magnitude bigger than the negative one. We have a longer field vector. Here we have a shorter field vector. So yeah, this one's plus, this one's minus, but this one's smaller. And this one's bigger. So they don't cancel. Right? So divergence is a way of measuring how on this region, on that region there, you're going to have a positive amount of flux, positive amount of boundary flux that you would measure on that region there. Right. So going back to our whole picture, positive amount of flux happening on this large region. We measure the flux on the boundary, but where it is the flux actually happening? Well, there's no flux happening at that location, right? The flux is zero at that point. The flux is zero over here for analogous reasons. The flux starts to get positive. Let me draw a slightly bigger region here. The flux starts to get positive in here. Just like with change, we measure the change on the boundary, but that's just an illusion. Where the change actually happened was perfectly clearly in the interior. The derivative is the thing it's telling us. The derivative tells you how much change is happening near a certain point. Same thing here. The flux is measured on the boundary, but that's an illusion. Measured there, but that doesn't mean that's where it's actually coming from. Where it's actually coming from is in the interior as measured by not the derivative, not change density, but by flux density. So flux density would be positive here, indicating that there's some positive amount of flux happening, like we talked about. Right? Divergence would be zero over here because, well, look at the picture and see there's the same amount of flux going out as there is going in. No flux, no divergence. Okay. All right. So I think this is a really useful idea. Flux density. It's very natural. And I guess I've talked about that enough at this point. So one more quick thing I want to talk about circulation. So recall with Green's theorem, we compute this expression here. Right, so line integral of a vector field around a boundary is a double integral of Green's operator. Let's talk about the object in question, the thing that we're computing on the boundary. So we gave this, the analog to this we named flux with Gauss's theorem, change with fundamental calculus. Here, I'm going to call this circulation. And the reason why is actually a pretty natural idea. But if you have a region, let me do it like this. Here's a region. And if you look at the boundary curve, right? And keep in mind what this integral here represents. One way to think about what this integral represents, a line integral of a vector field along a curve computes work if your vector field represents a force. But alternatively, if you think of your vector field as representing a fluid flow, this represents the extent to which the vector field is flowing along the curve. Now let's try to draw a vector field that's flowing along this curve. And, the curve is a boundary. The curve wraps around on itself. Right, so if there's a vector field that's kind of flowing along the curve, it suggests that the fluid that this vector field represents is, to some extent, some way, you got a little whirlpool situation going. Okay? So the value of this integral represents the extent to which the fluid is flowing along the curve that's making a loop. That's the the curve is making kind of a little circle. Certainly the tangent vector is going around in a circle. So the extent to which the fluid follows that curve, reasonable to call that circulation. The extent to which the fluid is kind of, going around in little circles. Okay. So anyway, the term is circulation. Very common term, and making an argument just like we did previously. Circulation is an accumulating quantity. That's why Green's theorem works. And therefore I can interpret Green's operator as circulation density. So I think the best foot in the door on all this stuff is fundamental theorem of calculus. I want to encourage you to look at this picture that we have. By the way, I forgot to email this picture to y'all. I was going to email y'all this before class started, and then I forgot. But I will email you this picture after class is over. Think about the fundamental theorem of calculus as it pertains to this picture, and persuade yourself that the derivative is a way of keeping track of where and how much the accumulating quantity of change is actually happening. Right? And then along those lines, divergence is a way of measuring, identifying where flux is actually happening, surface flux, boundary flux. And then along those same lines, Green's operator, I'm going to let you all think about this picture as well. Feel free to come and ask me in office hours if you'd like. Green's operator is a way of identifying where circulation is actually happening. And you measure circulation on the boundary, but that doesn't mean the circulation is happening on the boundary. My gosh, no, of course not. That's just where you measured it. Right? Where does the circulation actually happen? Well, it happens somewhere in the interior, and Green's operator is a way of telling you how much and where in the interior. Okay. All right, but start with the fundamental theorem of calculus. Get comfortable with the idea of a derivative being a density, and then apply by analogy to these other theorems. Okay. All right, where's my little thing? There it is. Okay, so let's do a little bit of physics. We're going to talk about fluids a little bit. There's different ways to interpret divergence as it pertains to fluids. I'm going to be fairly quick about this. Whoops, what did I just do? Hit the wrong button, sorry. There we go. So, there's an easy formula. Mass is a triple integral of density. And let's now imagine that this mass that we're computing as a triple integral of density here is a fluid, and that this fluid's flowing around. And I want to think of this as a fluid. This is a compressible fluid, so don't think water. Water has this annoying characteristic that its density is fixed, constant. It never changes, right? You go to the bottom of the swimming pool, there's a lot of pressure down there, and your ears hurt, but the mass per unit volume of the water at the bottom of the pool is pretty much identical to the mass per unit volume of the water at the top of the pool. It's weird, but anyway. So I want to think about different fluids. So, what fluid are we thinking about here? It could be that it's a gas. Gases are highly compressible, right? I also like to think of relatively discrete things like, imagine you have a swarm of bees. Well, each bee thinks of itself as an individual, right? But you could think of that as a kind of a fluid, right? They flow around in kind of fluid ways. And if you write down to it a glass of water, the water is actually a whole bunch. It's a swarm of a bunch of little tiny little particles, right? So all fluids are really made up of particles, right? So bees are particles too. So you can think of this as being a bunch of bees swarming around, or a gas or something like that. But not water. Don't think water. Okay, so make the observation that, here we go. You can take the derivative with respect to time on both sides of this equation and put a minus sign on both sides of the equation. You get this equation. And now let's think about, what is this negative dm dt? Well, if you have some region here, right, if that's your region over which you're doing your integral, computing the mass of stuff in there, negative dm dt says, well, how fast is mass leaving this region? In other words, negative dm dt is going to be flux. Right? Flux says, no, it's fine. Flux says to what extent is fluid flowing through the boundary, and of course through the boundary means out. Out means the amount of stuff that's on the inside is decreasing, right? So flux is just how fast is mass leaving the region. And of course flux can be computed with triple integral of divergence. So the nice interpretation that we get here is that because that's equal to that, and that's equal to that, and that's equal to that, we have an interpretation we can make then of divergence. In this context where we're thinking of fluids as, like a swarm of bees swimming around, or, fish. Fish go in schools, and you could view them as being kind of a fluid flowing around in the water. Divergence is a way of measuring, this thing right here, the rate of change of density. Well, the negative, to be more precise, is the rate of change of density. And so I like to call that local decompression rate. Right? So divergence, if you were to look at a vector field representing bees flowing around, divergence, something that looks like this, bees all kind of flowing away from one region would correspond to the bee density in this region going down. Right? If you think about it, that makes sense, right? So positive flux outward, positive divergence means that the bees are evacuating this region. That means bee density is less. Bee density is decreasing. So that's one way to think of divergence in context of fluids. I like that one pretty well. Here's a different way to think about it. Now this is really just a different set of assumptions that we're going to make. Not all fluids are like bees. Some fluids have the different feature of they can be spontaneously generated, spontaneously destroyed, right? So I guess, I don't know, bees. I guess you could think of bee, every so often the bee has baby bees, right? But it doesn't really fit very well. But you can think here, one of my favorite ones is light. Right? If you think about light, what is light? Light's made up of a bunch of photons. Photons are little particles that carry light. If you have a light bulb, that light bulb is spewing photons out, right? And lots of photons. It's creating a flow of millions, I don't even know, billions, trillions of, I don't know how to, my context of scale is not good for that, but lots and lots of these little particles are just spewing out of a light bulb. So the light bulb is creating a fluid. Those photons that are coming out of there were not previously there. So there's a spontaneous generation of that fluid. Right? Well, the weird thing is, if you think about it, if you have a light bulb on, such as one of those, it's not depleting of photons. It's not like there's an existing quantity of photons in there, and the photon density is just decreasing. Right? If there were bees flowing out from there, then okay, well, come on, they're gonna run out of bees eventually, and the bee density must be constantly going down, and eventually there's no bees left. With a light bulb, it's steady state, right? It's creating photons. Okay. All right, so that gives rise of a sort of different assumptions and different way to think about what the fluid is doing. So here's a different way to think about mass. I can think of mass as a triple integral of density. I'm thinking of density as mass per unit volume. Okay. Again, let's take a time derivative of both sides of the equation, which I'm wanting to do in that special way there. And now let's think about this scenario. What is the rate of change of mass? Well, if you have, let's think of this again. I like photons. I like it's easy to visualize photons. Spewing out of a light bulb. But I want to think of this in terms of mass. So let's imagine that there was some scenario, some sort of mythological scenario where mass is spewing out of some region, right, in a steady state way, right? How much mass is spewing out of the region would be flux, right? So you have this region, mass coming out. The process in a steady state of the mass coming out of the region would be flux through that region. So that's flux. Flux, of course, is triple integral of divergence. That gives us this different way to think about divergence. This says per unit volume, what's the rate that mass is coming out as being spontaneously generated in that region? So per unit volume, what's the rate that mass is being created? And so let's see here. The per unit volume makes this a density, and how much mass is being created, part of that. Oh, that made that kind of disappear. Well, that's okay. How much mass is being created, we call a source. It's a source of whatever this fluid is, whatever the mass, whatever it is. So source per unit volume, otherwise known as source density. So this is another term that you'll hear a lot, is people will talk about field sources and field sinks. So sink is the opposite of a source. A source means stuff is being spontaneously created and spewing out in all different directions. A sink means that the fluid is flowing in towards some region and just kind of disappearing, like water going down a sink. Yeah. Anyway, source density and sink density. So you'll hear these terms quite a bit, sources and sinks. Okay. All right. Moving along now. We've got a few minutes here. We're not going to finish the gravity part of this discussion. It's too bad. But I want to talk about gravitational fields. So here's the formula that you all saw in, I don't know, when I was in high school. It was 9th grade physical science class. Hopefully you all have seen this formula before for gravity, right? Everybody knows the force of gravity is an inverse square, so it's 1 over distance squared. Right? And it's proportional to the masses of the two objects, and then there's this thing, Newton's gravitational constant, some number. Okay. All right, so I make the observation that here's a way to write that as a vector field. So this looks kind of wrong because you see this cube down here and you think, wait a minute, I thought it was inverse square. Why is this inverse cube? But it's not. This is actually inverse square because what we have here, let me rewrite this a little bit. I would like to rewrite this as negative G M1 over magnitude of x squared times x over the magnitude of x. So in fact, the cube, right, is really kind of hiding two separate terms. This one factor of magnitude of x is just really part of a unit vector. This is just a unit vector indicating direction, the direction of the gravitational field points. That's not really part of a magnitude. This makes a unit vector. So what we have is an inverse square magnitude and a unit vector direction. So anyway, a little bit of an illusion there. The other thing that you might have noticed is that M2 disappeared. What happened to the M2? The formula for gravity, if I have two objects, it's proportional to the product of the masses. Okay. But I don't want to think about the actual gravitational force between two objects. I want to think about one object at a time and what is it that this thing creates. By itself, this one mass creates a gravitational field is something I want to talk about. So what we're going to do is we're going to define the gravitational field of a given object to be the thing created by that object, which, when you multiply by the other mass, gives you a force. So you might think of it as we're going to define the gravitational field to be the gravitational acceleration field that's created by a single object. And then that acceleration times this mass gives you the resulting force. So anyway, that's where the other mass goes. Anyway, this is what we're going to use as the formula for a gravitational field. It's very important to think of a gravitational field as a vector field and not as just a high school scalar formula, because a gravitational field is it's got direction. The direction's important to what the gravitational field is. So this is the formula, and amazing calculation that y'all have actually already done is that the divergence of this gravitational field, and let me do it like this, the divergence of that gravitational field is 0. Y'all did this calculation already. You did this back in chapter 4 in the section on partial derivatives, and one of the exercises was compute this thing called divergence, which at the time I told you that we're not ready to talk about what this thing is yet, but it's something you can compute with partial derivatives, and it's going to come up later, and here we are. So anyway, y'all have already done this calculation. I encourage you to go back to chapter 4, section on partial derivatives, find where you computed the divergence of a vector field that looks exactly like this. And notice that you came up with 0. And I'm out of time, so we'll pick up here. It turns out there's a really amazing consequences of this fact. Some amazing physics that you can do because the divergence is 0. We'll see that next time. Y'all have a good day.